Okay, lecture number 18. In the previous video, we have seen that in QPSK we may have 180-degree phase shift, and let us see how to identify whether the phase shift is 180 degree or less than that. Consider this point. Here, your phase shift is 180 degree because suppose you extend this waveform here, and after that you fold this particular black waveform, you will get this waveform, right? Means fold means you are taking the negative of that. So negative means 180 degree phase shift. So this is the 180 degree phase shift transition over here. Suppose you have a waveform like that, and at this point you have a phase shift like this, another waveform. So in this point you don't you don't have a 180 degree phase shift. This is not a 180 degree phase shift. This is some arbitrary phase shift, maybe 70 degree, 80 degree, but this is not 180 degree. This point you should note. Okay, we have been discussing the organization of digital modulation. We have discussed the BPSK under the passband modulation scheme, and we have also discussed the QPSK, and we have started the offset QPSK, OQPSK. So before discussing the OQPSK, let us discuss some more details, QPSK. So suppose you have the data stream, it is coming from a source, and you have combined 2 bits at a time to create one symbol, and let us assume the red color bits are the in phase bit and the blue color bits are the quadrature phase bit. So after receiving the data sequence, we are mapping them into a specific waveform, and then we have the in phase component, and we have the quadrature phase component. So in QPSK, what we are doing, we are combining these two in phase and quadrature phase component, and we got the QPSK waveform. So observe here, in this case your in phase component has transition from 0 to 1, and in the quadrature phase component has a transition from 1 to 0. So at the sampling instant t, we have a 180 degree phase shift, and in the previous lecture we have seen that this create a problem in the band limited channel. Due to band limitation of the channel, you cannot detect the phase very accurately, so that's why you have the concept called offset QPSK. So in this case we have also the same data stream coming from the source, and we have the specific in phase and the quadrature phase waveform for both ones and zeros. But in case of quadrature phase component, it is shifted by t by 2 second. So this gap is t by 2 second, and this quadrature phase component is shifted by t by 2 second. Now consider the first sampling instant, that is this one. In this case, or in this instance, suppose your data is 0 1. This is data 0 1. So in the constellation diagram, you are in this position. Sample at 3t by 2 second. That means here, observe that your quadrature phase component has not been changed. This has not been changed, but in phase component has changed, because at the sampling instant t, the in phase component was 0. So this is was 0, but at the sampling instant 3t by 2, your in phase component is 1, right? So this is 1. So this was the data at t second, and at 3t by 2 second your data is 1 1, shown 90 degree phase shift. This is 3t by 2 second. So here is a 90 degree phase shift. Now you have to sample at 2t second. Now at 2t second, your in phase component data has not been changed. It is still 1. That means this data has not been changed, first red one, but your quadrature phase data has been changed. At 3t by 2 second, it was 1, this one, but at t second, this t second, 2t second, it become 0. So it has changed. So your new data is 1 0. So 1 0 is your new data. So this is the data. So at 2t second, this data has changed to 1 0. That means 90 degree, another 90 degree phase shift. Second, your data is 1 0. So from t to 2t, that is one sampling gap, your data is changes from 0 1 to 1 0 by 2 successive 90 degree phase shift. So in the QPSK, there was no need to sample at the 3t by 2 second or 5t by 2 second, but in this OQPSK, you have to sample at that point also. But you don't have any 180 degree phase shift. You have maximum 90 degree phase shift. So in case of QPSK, OQPSK, not QPSK. You have to delay the quadrature component by t by 2 seconds, and the maximum phase change is plus minus 90 degree. Now the representation of a QPSK signal. So S dash T is the in general any passband signal, and ST is the baseband equivalent model of this signal. So this is the constellation diagram for the QPSK signal. Now the baseband model or baseband equation of the QPSK signal is this one. So in this baseband equivalent model, this AL convey the phase information. So this AL could be any of them, this value, which has a amplitude A and the specific phase, right? Now the passband equivalent of this QPSK signal is the real part of this CT, and with e to the power j omega t, omega naught t, where omega naught is the carrier frequency. Now in case of OQPSK, you have to combine two pulses which are offset by an amount t by 2 seconds. For this OQPSK, you have to consider both the even and the odd part of the data bit separately. So let us assume that the even bits are the in phase bits, that the red one bits, red color bit, and the odd bits are the quadrature phase bit, that is the blue color bits. So the signal CT can be represented. So this is the expression. Here one pulse shape is shifted by t by 2 seconds, then another. In this case we have already included this J phase term here. So this BL, it could be plus A for the data bit 1, and it could be minus A for the data bit 0. Now for the passband equivalent, you have to just take the real part of the CT e to the power j omega naught t. Okay, now another very beautiful concept known as a trellis diagram, which is very important to represent the OQPSK, the phase changes in the OQPSK.